For this Pencast, we'll look at power series, the exclusive topic of section 11.8. As introduced in class, the power series are series in this form right up here, where you have a series of constants, and there's no pattern to the constants necessarily. What defines a power series in X, our first power series will be power series in just X. They're identified by X. If I add in an X here to the power of 0, we see that X occurs in every term following the integer progression, like every other series term. Additionally, the only other thing in each term is this constant right here, C sub 0, C sub 1, C sub 2. And as it expands out, as we mentioned, looks exactly like a polynomial. So there's nothing else except x to the k terms and the constant, the coefficients. As we look down right here, generally, every Maclaurin series is a power series in X, and that's easiest seen by looking at the general term, where all of this right here in this general term comprises C sub k, and of course we have x sub k, and that occurs in every term of a Maclaurin series, so clearly they are power series in X. And then other examples are up here. Again, just X in every term, everything else is the coefficient. Determining convergence for power series in X and power series in X minus X sub 0, which we'll look at a little bit later, but determining convergence is a rather tricky process, requires 3 steps, but we'll get to that when we look at the examples. On this slide, we're looking at theorem 11.8.1, which talks about the cases of convergence. As a point of fact, every power series in X converges at X equals 0. So 0 is always a point of convergence for all power series in X. If you substitute X equals 0 into a power series in X, you simply get 0 plus 0 plus 0 plus 0 forever. So clearly that converges to 0. As we read this paragraph right here, you can see that perhaps the convergence is an interval centered at X equals 0. However, the interval could just be that. So it could be an interval with width 0. So it's only a point. That would be this case. The other one is that it converges for all X. So your interval is infinite, or it converges for X equals 0 plus or minus some value, in which case you have this case here, which would be a finite interval. Now the radius of convergence, just to make sure when we're using that vocabulary we know what we're talking about, the radius is best illustrated in the third part of the graphic right down here. That's really the radius right there. So you really have X equals 0 plus or minus r. So the radius is that. The interval is the whole thing, and the radius is just the plus or minus side of it. So looking back up at theorem 11.8.1 is just sort of the verbal summary of the paragraph and the graphic. So case A, the series converges only for X equals 0. Series converges absolutely, hence converges for all real values of X. The series converges absolutely and hence converges for all X in some finite interval. What you'll notice every time we saw this right here, and just like we said in today's class, the ratio test for absolute convergence is the key. So here we'll look at the example 1 with the 4 parts, and each of these series behaves differently with respect to convergence. So we'll look at it. Because the ratio test for absolute convergence is the key, I brought it up here on every slide. Commit it to memory. That thing is a brain tattoo for the rest of the course. So let's look at A. And we know how the ratio test works. We look at the general term, which is given to us, X sub k, and we look at the k plus first term, which is X to the k plus 1. Plus 1. Then we create the limit k goes to positive infinity, the k plus first term, on the numerator, and then the kth term on the denominator, or the general term, absolute value, and let's see what happens. So limit k goes to positive infinity. you can pretty much tell we don't need any algebra on this one, that it boils down to the absolute value of x. So that's what this limit equals. So the limit is just the absolute value of x. So either way, it's like, boom. So my limit isn't a value, it's an expression involving x. That's where the interval and the radius of convergence comes in. So when you're done with the limit, it should be an expression in x. And then ask yourself, for what x does this expression, or whatever the limit is, comply with this? So let's look for convergence right here. So I want the limit to be less than 1. So since our limit is the absolute value of x is less than 1, where is the absolute value of x less than 1? An Algebra 1 flashback will show that an absolute value inequality, which is less than, forms a conjunction where x is bounded by 1 and -1. Done. And you thought that was the end of it. Nope. So we've established thus far that the example in part A has a row value, a limit of the absolute value of x. So we know that that limit complies with convergence when that limit is less than 1. So I want the absolute value of x to be strictly less than 1. Bam. So I have this interval. So I know I have 0 plus or minus 1. All power series in x converge at 0. This is my radius, but I can't say this right now because I have to look at the endpoints. So I need to consider the final step, why this is sort of a multi-step process. I need to look at x equals 1, boom, and look at x equals -1 explicitly. Now, why do I have to do that? Well, if this is my limit right here, notice when the limit is equal to 1, it's inconclusive. So you can't let that go and just go plus or minus 1. Because depending on how you interpret that, you're either including 1 without checking it, or you're excluding it when it should be included, or including and excluding on one side, not the other, etc. You have to look at the endpoints. If there's a point of inconclusiveness, if a value for x results in a row value of 1, then you have to sort of stop what you're doing or continue what you're doing and look at x equals 1 and x equals -1, or whatever value makes the row value 1 explicitly. So we need to look at x equals 1 here on this limit. So, and as a reminder, we do look at x equals 1 in the original series right there. So just pop it in, stop and look at it. And every convergence test you've looked at up to this section is fair game. So when x equals 1, our series looks like, let's see, 1 to the 0th. So we got 1 plus 1 plus 1 plus 1. That was difficult. Boom. And we're pretty sure that thing diverges. So diverges. So x cannot equal 1 in my interval. Remember, our goal is to create an interval of convergence. Always centered at x equals 0, but we need to know how far the interval goes on both sides, and as importantly, if we include the endpoint on both sides. So x equals -1, -1 to the 0, looks like that's going to go with 1, -1, plus 1, whoops, minus 1. Let's see, 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. And we know that one diverges also, diverges. So x cannot equal -1. So our radius is 1, and our interval is -1 to 1 exclusive. Done. On to part B. As said, we can look at the series and go, I wonder what's going to happen with this one. But you know what? Dive right into the ratio test for absolute convergence. Find out what x value makes your limit comply with convergence, which would be case A. Double check that there's no inconclusive, or no value for x, that results in an inconclusive case C. Otherwise, you have to look at them separately. So let's dive into the ratio test for absolute convergence and see what's up. U sub k is just the general term. x sub k over k factorial. That's the k plus first term, k plus 1 over k plus 1 factorial. Limit k goes to positive infinity, the k plus first term over the kth term, k plus 1 factorial over x to the k over k factorial absolute value. And we've done enough of these. If we can do it in our head, complex fraction, outers over inners, cancel exponent factorial, I get limit as, k approaches positive infinity of x over k plus 1. You are doing absolute values, so that's part of it, and that is your limit. So now that's our limit value. Take a look at the cases for the ratio test for absolute convergence up here. What happens? Well, remember, x is a value, and k plus 1 is an integer progression. So we look at that. And we notice that when k goes to infinity, this limit is equal to 0. So it is this case here for all values of x, irrespective. Therefore, it converges absolutely, therefore converges. The radius is, I hate to use equals, infinity, and the interval is negative infinity to positive infinity. Done. Because there's no value for x that results in any inconclusiveness, aka case C, that limit is 0. You're looking at it. So that converges for the infinite all real number interval. In the interest of time, I'm either going to have you look at this intuitively or say you do the algebra, but the limit as k approaches positive infinity is going to be quantity k plus 1 times x absolute value. That should be obvious given all the work we've done with this monomial form and the factorial. When you put the k plus first term over the kth term, you get the kth terms canceling out, leaving you only one more, the k plus 1 on the numerator. So we get this. We know that's equal to positive infinity. It's clearly a case B. This series diverges. However, the radius, you don't just say divergent when you're looking for this. Typically, power series will ask for the interval and the radius. So the interval is 0 only. Interval is 0 only. Playing kind of fast and loose with the word interval there, but it is 0 only. Semicolon, radius is 0. Done. Again, in the interest of time, I'm simply going to tell you that the limit as k goes to positive infinity is the absolute value of x all over 3. You can read this in the textbook or just algebra it out. I just didn't want to spend all the time on the Pencast duking it out algebraically. So we know that we're looking for the radius and the interval of convergence on this one. So we do have like cases going on here. So we look for this. Case 1 is the convergent case. So we know, when is that true? Well, we know that's true when this limit is less than 1. That happens when the absolute value of x is less than 3. So as we know before, conjunction 3, negative 3, and now we have to look at the endpoints separately. And that's where it gets interesting. Again, when you look at the endpoints separately, you're plugging 3 and negative 3 in any order, it doesn't matter, into the original series, simplifying it as much as you can, and then looking at it with all the convergence tests that we've done to date. So let's consider x equals negative 3. So remember, that goes into the original series in for x right there. And what do we get? We get negative 1 to the k, negative 3 to the k, over 3 to the k, k plus 1. If I'm not mistaken, I can do that and then cancel, and I should be able to get 1 over k plus 1, which you know is going to be the divergent harmonic series. So we can say divergent harmonic series. So x cannot equal -3, so -3 will not be in our interval. So looking at x equals 3, you might already know what's going to happen. You're not going to get this little simplification. You're going to get the alternating harmonic series. So you're going to get what? -1 to the k, 3 to the k, 3 to the k, k plus 1. Looks like, right, do that, -3 to the k, 3 to the k, you're going to be left with -1 to the k over k plus 1, which is the convergent alternating harmonic series. So x can equal 3. So my interval is 0 plus or minus 3. You'd say your radius is 3 and your interval is -3 to 3 inclusive on that, exclusive on that. I'm really not feeling the love on this form because it doesn't really specify if your endpoints are included or not. So I would have to say that your final conclusion should be these two things. Always realizing that 0 is a point of convergence, specify the radius, and then use interval notation. Not feeling the love on that because of the ambiguity. Okay, this slide looks at power series in x minus x sub 0. So we're looking at this phrase right here, power series in x minus x sub 0. And then here's the similar introduction part like we did power series in x. Again, we have our series of constants. They don't follow any pattern necessarily, right? However, the quote-unquote polynomial part, the variable part of the polynomial kind of looks like unsimplified factored form right there and there. So it's really, to me, it looks like a partially expanded polynomial. It's not quite expanded all the way. It's not quite factored all the way. So you're sort of adding constant times binomial to the nth power. So it's half expanded, half factored form. But it is a polynomial, and the variable part is this expression, x minus x sub 0 to the k. So we would say it is centered at x sub 0. And again, it's here somewhere. All Taylor series are power series in x minus x sub 0 right here. More generally, the Taylor series, boom. And again, for the same explanation, this all comprises c sub k, that's a weird looking c, and then we have our binomial looking part, x minus x sub 0 to the k, etc. So every Taylor series is a power series in x minus x sub 0. So we have this. It's kind of like substituting x minus x sub 0 into the power series in x. So, oh, it actually says it right here. If x is replaced by x minus x sub 0, then you get your power series in x minus x sub 0. So theorem 11.8.2, same idea. It's convergent. Converges absolutely for real values of x, or it converges for some finite interval. If you read it and then you flip back and forth, you're like, oh, this is the same. We just have x minus x sub 0 instead of just x. So you can't say that every power series in x minus x sub 0 converges at x sub 0. It converges at whatever that number is. So if your power series contains, for example, x minus 5 to the k, then x sub 0 is 5, and 5 becomes the center of your interval. And that's illustrated right here. So you could think of power series in x as x minus x sub 0, where x sub 0 is fixed at 0, but then you're saying 0 a lot. So here, since you have this binomial form for the variable part, the constant is the center of your convergent radius. Guaranteed it will converge at x sub 0, whatever that is, but your job is to find out how far beyond that, if at all, does the radius extend? And again, your cases are, it converges only for that value, which it definitely will. It converges absolutely, so you know what the game is, ratio test for absolute convergence, etc. For all real values of x or some finite interval. And let's look at one example. The algebra on this one is dicey, so we are going to go over it step by step. It shouldn't seem dicey because the other ones were like, oh yeah, ratio test for absolute convergence. We almost knew what was going to happen once you set up the ratio test. So the algebra was kind of blah, blah, blah. This one's dicey, so let's go for it. So general term, pretty much handed to us. It's x minus 5 to the k over k squared. K plus first term, x minus 5 to the k plus 1 over k plus 1 quantity squared. Look at the limit as k goes to positive infinity, k plus first term over the kth term. So what do we get? Oh, compound fraction, that's going to be fun. X minus 5 to the k plus 1 over k plus 1 quantity squared, all over x minus 5 to the k over k squared, and we are absolute valuing that. All right, what are we going to do? What are we going to do? If I skip a step, I'm going to make an error. Oh, goodness. Outers over inners, so I got k squared, x minus 5 to the k plus 1, that's the product of the outers, over product of the inners, x minus 5 to the k plus 1 squared, absolute value. When you're looking at this, you're like, this doesn't make any sense. No, I don't necessarily get any cancellation. I guess I can cancel the x minus 5. So I get limit, k goes to positive infinity. I'm going to bring this out, right? I'll do this in yellow. I get rid of this and this. That would give me what? X minus 5 out in front, and then k squared over k plus 1. I don't know why I was writing that. Quantity squared, and we are still absolute valuing. So I'm not seeing where I can take a limit or see what's happening. However, since k is a positive integer, right? The whole thing squared, this is always going to be positive. This is always going to be positive. That makes the absolute value not necessary. So limit k approaches positive infinity, x minus 5 absolute value times limit k goes to positive infinity, k over k plus 1, whole thing squared. Life is good. I know this limit is equal to 1, so that means my limit here, that's very, very messy on the notation, my apologies, is x minus 5. Boom. So the ratio test for absolute convergence you might have to yield a little more algebra mojo for power series in x minus x sub 0 instead of power series in x, but certainly not beyond what we can do. So if that's our limit value, then we look up here for conclusions. So where is it less than 1? And you can tell it's like, okay, I follow the process. It's less than 1 when x minus 5 absolute value is less than 1. Do a little algebra 1 conjunction here. X minus 5 less than 1. Add 5 to all sections, and I get 4. Boom, x, boom, 6, which is an interval centered at 5, which you knew was going to happen. So we have to look at 4 and 6. So pulling the example and the last little bit of the work from the last slide, all we have to do is what we did before, look at x equals 4 and x equals 6, So substituting x equals 4 in here, always into the original, I get negative 1 to the k over k squared. That should be obvious. That's an alternating p series with, no, hang on. I can't really say it's an alternating p series, but I know this is a p series with P equal to 2, which I know converges, and I know it's alternating here because of this oscillating factor. Well, if I absolute value it, I know that converges absolutely, which makes it convergent. So I am going to include x equals 4 in my radius. Now looking at 6 up here, plug that in there, we get, that's just 1 to the k, so that's 1 over k squared, which is a normal convergent P series. Again, P equals 2. So I'm going to include x equals 6 in my interval. So my radius is 1, and my interval is 4 to 6 inclusive. And that's a wrap. The takeaway on this is going to be ratio test for absolute convergence. See if you can make any conclusions right off the bat, or if the limit sometimes complies with case A in the ratio test for absolute convergence, then that's your sort of primary interval. Then take a look at the endpoints. And the endpoints, again, plug into the original and you just stop and look. Any convergence test that we've done to date will help for the last part of the ratio test for absolute convergence. All right, the end.